Hey guys, welcome back to my channel. Long time no see. Today let's talk about the relationship, connections, and differences between three measures: population standard deviation, sample standard deviation, and standard error of the sample mean. Okay, population standard deviation, sigma, sample standard deviation, S, and standard error of the sample mean, sigma subscript x bar. Okay, because many of you asked me to talk about t-statistics and the t-distribution. I think you can better understand t-distribution or t-statistics once you understand these three measures and the relationship, connections, how can we use one to approximate the other. Okay, so yeah, without further ado, let's get into it. Okay, so let's talk about the relationship, differences and a correlation between sigma, which is population standard deviation, and S, sample standard deviation, and a standard deviation of x bar, which is also called standard error. Okay, so sigma is population standard deviation. S is sample standard deviation. Sigma subscript x bar is standard error of the sample mean, or you can call it standard deviation of the sample mean. Okay, so now let's use the variable x. So let's look at how to calculate each of this. This is a population parameter. This is a value we can calculate using population data. So this is a population parameter. And this is the value we can calculate using sample data. So this is a sample statistic. But this one is the standard error or standard deviation of x bar. Now let's look at how to calculate these values and what the relationship between any two of these values, what the connections. So suppose we have the variable x, I don't know, maybe it's test score. And if we have population data, so population contains this many observations. I have this many observations, maybe 10,000, it's a very large number. So now if I have the data, so I have this variable x, and then I have for each, maybe for each student, I have this many students, I have this n student. For each student, I get a test score. Now, student number 2, I can collect the test score. Right, all the way to student number n, I can collect a test score x sub n. So based on this n observations, I can easily calculate the population mean, right, which is mu. But here, okay, let me write it here. So sum all the values of x, right, divided by total number of observations, I can get the population mean mu. And now the population standard deviation measures the dispersion of the values of x deviate from the average. Right, so if you can visualize the data like this. Right, this is x, and average maybe here. Right, so any point along this x-axis is a value of x. Right, so how the values of x deviate from the average. So we can use the measure population standard deviation. So now sigma equals each value minus average squared. Right, distance squared. The second value minus average squared, plus all the way to the last value minus average squared, and then divided by total number of observation n. This is a variance, but you want to have a standard deviation. So to take a square root of this whole thing. So you can simplify this into square root of sum deviation from the average squared divided by degrees of freedom. Now here we have population data, so there's just the population size n. Okay, so this is how we calculate population standard deviation if you have population data. But the thing is, we don't always have, or almost we never have population data. We don't need population data, right? We just use the sample data to estimate the population parameter. So this is how we get the population standard deviation sigma. So now let's look at how to calculate the sample standard deviation. Okay, let me write it here. So sigma equals sigma of x. I can use sigma subscript x, right, equals square root of sum each value of x minus average of x squared divided by n, number of observations in the population. Okay, so now let's look at the sample standard deviation. So sample standard deviation, as the name suggests, it's a sample, right? It's based on sample data. So now out of this n observations, this is population, I can randomly select a sample contains small n, or little n observations. Out of this n, I choose n. So this is my sample size. Maybe the sample size is 16, maybe it's 20, maybe it's 100, maybe it's 1,000, maybe it's 500. So this could be the number of observations in the sample. So out of this many students, I randomly select this many students. So now my sample data will look like this. 1, 2, 3, 4, all the way to n. And then have this x sub I. Randomly select student number 1. I have this test score x1, x2, x3, x4, all the way to x sub n. And then out of this n observations, I can compute the sample mean, which is sample statistic. So now the sample mean is sum the value of x divided by lowercase n, right? So this is what we just use the letter x bar, right? This is notation to denote the sample mean. And now we have the sample mean. Let's calculate the sample standard deviation. Okay, the sample standard deviation is based on sample data, this n observations. So it's the same idea. Right? Standard deviation is a measure of dispersion. It's the same idea. Sample standard deviation measures the dispersion of the value of x deviate its own average. Right. So you can show this graph. So this is x. And then the average is x bar because it's based on sample data, so just use x bar instead of mu. And any point along this axis is a value of x. So sample standard deviation measures how the value of x deviate from the average. Right? So mathematically, so the formula to calculate sample standard deviation, we just use S equals each value of x minus its average squared. Right, plus the last value of x minus average squared divided by now degrees of freedom. So I have a whole video talking about why here we should divide it by degrees of freedom, which is n minus 1 here. Okay, check out that video of n minus 1. And you take a square root to get the sample standard deviation. So this can be reduced to or simplified into this formula. Xi minus x bar squared divided by n minus 1. So this is how we calculate sample standard deviation. Okay, so now I write here S, you can use this notation S subscript x because this is a standard deviation for this variable x, and it equals square root of sum each value of x minus x bar squared divided by degrees of freedom, which is n minus 1. Okay, so now what is the relationship between these two? So let me tell you the relationship between sigma and S. Most of the time we don't have population data, let alone the population standard deviation. So most of the time we don't have any population parameter, right? Because we don't have population data. So what we do is we rely on the sample statistic, right, to estimate the population parameter. So most of the time this is unknown. So let me write here. This is unknown. Sigma population standard deviation is unknown. And then what we do is we use sample standard deviation to estimate the population standard deviation. So this sample standard deviation is approximately equal to population standard deviation. This approximation only true. This approximation only makes sense when the sample size is large enough. When this sample size is large enough. So large enough statistically, that means when there are at least 30 observations in your sample. Okay, so that means we can use S to estimate population parameter, or we can use S to replace sigma, right, when sample size is large enough. Okay, sample size is large enough, S is approximately equal to sigma. Now let's look at the standard error of a sample mean. So this is a little bit different because now we don't have data that makes sense theoretically. Okay, so now in this case we don't have data. Because in practice we only have one sample. Right, we only have this one sample, but in theory we could have so many samples. Right, when we talk about central limit theorem, we talk about that. So out of this many observations, I randomly select this many. So out of this many observations in the population, and I choose n, right? This is the number of samples. So for each sample, you should have a sample mean. So if you organize all the sample means into probability distribution, you get a distribution of x bar. Right, so the central limit theorem, check out the video about central limit theorem. Okay, I have a the most intuitive understanding of central limit theorem. Check out the video before. So now, this follow normal distribution when n is large enough. Okay, so this, if you supposedly or potentially in theory, you have this many samples, and then for each sample, you can compute a sample mean. So if you organize all the sample means into a probability distribution, it follows normal distribution. And central limit theorem says the average of the x bar equals population mean. As long as you have all the possible sample means, the average of sample mean always equal to population mean. And the standard error, that standard deviation of this variable, we can use sigma standard deviation subscript x bar is the standard deviation of x bar. Okay, and this, we have very famous, very useful square root of n rule. So that's equals population standard deviation divided by square root of n. So now, so this, let me use this color to write here, sigma subscript x bar, that's standard deviation of x bar, equals population standard deviation divided by square root of sample size. Right, this is the sample size, number of observation in the sample. And this, because you know the relationship between S and sigma, right? If sigma is unknown, we can use sample standard deviation to approximate sigma. So that also equals approximately equal to S over square root of n only when n is large enough. Okay, we talk about the n is small in the next video because some of you ask me t statistic or t distribution. So that's kind of introduction, prerequisite knowledge. Okay, prerequisite knowledge to understand t distribution. So let me give you a summary here. Let me write here. Oh, now we have population. This is population size. Population size is n. We don't need to know, right? And we have population mean. We have population standard deviation. And then we have sample. Sample size is n, sample mean x bar, sample standard deviation s. And now we have the distribution of sample mean, right? This is the sample mean. Sample mean here, which is x bar, right? So number of sample means, in theory, there will be this many. Out of this many observations, you choose this many observations. C, n, choose n. This is the number of combinations you will have, right? Order does not matter. So this is number, this is combination formula. You should know that, right? So that NCR, n factorial, r factorial times n minus r factorial, right? This out of n objects, you randomly select r object. This is the total number of combinations. A number of different ways you choose r out of n. Okay, so this is a number of samples, and average of sample. This number of samples. Each sample you have supposedly, right? Each sample you have sample mean, and the average of sample mean will be mu. So that's mu subscript x bar. Mu subscript x bar. If you have all the sample means, you will find this always equal to the true population mean. The true population mean. And standard error of x bar, we use sigma subscript x bar equals sigma over square root of n. So when sigma is unknown, or when n is large enough, and this equals s over square root of n, because again, so we can use s to approximate sigma when sample size is large enough. Okay, when sample size is large enough, and this n is sample size, right? So this is the sample size of sample, this is the size of population, right? Population size and sample size. Okay, so now for x distribution of x bar if we know average and if you know standard error, which is s over square root of n when n is large, right? And then you will calculate the probability that x bar in any range. Or if you are given a probability, you can you know how to find the value of x bar, right? Okay, so let's stop here for this video. And next video we'll talk about what happens, what should we do when n is small and the sigma is unknown. Okay, when n is small and the sigma is unknown. So when n is small, if sigma is unknown, we can use s to approximate sigma. Right? We can use s to approximate sigma only when n is large enough. But what if sigma is unknown and n is less than 30 or is a small sample, right? So that's why we need t statistics or t distribution. Okay, hope you find this helpful. So the next video is about t distribution, t statistics. Okay, so as I said in the video, that when we have small sample, the number of observations in the sample is small, and also the population standard deviation sigma is unknown, and then it's time for us to use t statistics or t distribution, right, to convert the value of x into a t value. Okay, so we'll talk about that in the next video, so stay tuned. Any questions, let me know. Okay, hope you enjoyed today's video and learn something. See you next time. Bye.